Hello everybody, this is Andy Pils on day 25 of our astronomy unit, and in today's lesson we're going to be talking about the Hertzsprung-Russell diagram, which shows the characteristics of stars in the ESRT, and then we're going to be going over the Star in a Box virtual lab, just some of the glitches that I thought existed, and then some of the workarounds around working remotely. So just really quick about this diagram, we've looked at it in previous videos. There's another video from another science teacher that goes over this diagram in more detail. But just remember the main difference between stars is just the initial mass, right? How much mass is in that nebula that formed into the star, and the amount of time that has passed since the star formed. So we're looking, if you look on the y-axis, the luminosity is logarithmic, meaning every big increment that's labeled here, instead of adding regular increments, because usually in a graph we'll say, use regular increments, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is logarithmic, meaning instead of adding, we're multiplying by 10 each increment. So it goes from 1 to 10. Then we're going to multiply by 10 and we get 100. Then we're going to multiply by 10 and get 1,000. Then multiply by 10,000. So these stars up on the top, they are almost 1 million times as luminous as our sun. It's pretty intense. We've seen a logarithmic scale before in the ESRT. It was when we were talking about the particle size of sediments. Again, this is logarithmic. And if you look here, the smaller increments, they count by the lower labeled increment. So if this is 1, or let's say if this is 0.1, the next line up is 0.2. The next line up is 0.3. The next line up, oops, I went the wrong way, is 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Then we get to 1.0. Then we count by ones. 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we count by tens, 20, 30, 40. So that's what's going on this Hertzsprung-Russell diagram, which shows us the characteristics of stars along with the temperature, which corresponds to the, or the color, which corresponds to the temperature that the star's surface is in Kelvin. So here's the activity for the day, the Star in the Box activity. The link here will give you a guide for this activity, so it has instructions and it will walk you through it. Just know that you can't draw in this, but you can draw in this. So in the instructions here are saying, you will notice a diagram showing a sequence that describes the different stages of a 1 solar mass star, which is what we're starting on. If we open the lid, you'll notice that we have a 1 mass sun star. The rectangles show different stages of the star throughout its cycle, and the arrows represent the main stages from one stage to the next. So using the same format, rectangles for stages and arrows to describe the main changes from one stage to the next, describe the life cycle of the other 2 stars. So let's take a look at this first. Now here's the thing, I thought this was a glitch before when I see the time so quickly went to 10,000 million years and then very slowly went up as the star was changing. I was like, I think something's wrong with my computer. But in this simulation, it says stars can take billions of years to go through their lives, with the dramatic events taking place in relatively short periods of time. In the animation, we speed up time when the star is not really changing much and slow things down for the dramatic phases in a star's life. So this will give you an idea of the different sizes that it grows to, the different masses, the different luminosities. But you can also take a look at this data table, and this will also give you average data for that mass of a star during these different sequences. So even though it took a long time in that simulator for me to watch the star go from its red giant phase to its later red giant phase, we know that most of this star's life took place in the main sequence phase, because we see it in our data table over here. And then in the later stages, the white dwarf, it would have just taken a really long time for the very last of that energy to have been fused together to turn into a black dwarf. So we can up the mass, and when we get more massive, you're going to see some pretty explosive things. So once we reach 10 times the mass of the sun in not so much time, we saw a supernova. But then if you look at the data table, after the supernova happened, this would be right after it became, well, red giant would have happened really quickly, and then it would have taken a really long time for the neutron star to ever end its life, which is why, whoopsie, the data here will read, what number is this? 12,000 million years. Even though when we watch this, the sun went from starting its life cycle to ending its life cycle in just about 27 million years, which isn't that much compared to the length of life of our sun. So you can add some shapes. Here it says to discuss those changes that you see in the diagram. So I would just add shapes right here to your diagram by adding, and then you can type what you see, and then you can also add arrows to your diagram. But I would just label for your teacher, just so they know which ones you're talking about. You might want to talk about a 10 and 20 solar mass star here. 10, 20 solar mass star. And then you'll start your diagram like that to show your thinking and your progress through this activity. That's it. So we'll just go over a couple more practice questions before I let you go for the day. Describe the relationship between temperature and luminosity of main sequence stars. So we're comparing the temperature on the x-axis to the luminosity, and here's all of our main sequence stars. So if you look at this pattern, as we move from right to left, that's something that I didn't mention before, the temperature is decreasing. So, I'm sorry, it's increasing. So even though usually when we're moving towards that y-axis, we would think that we're moving towards 0, but on this table, the temperatures are flipped. So as the temperature of the star, if we're moving up this way, the temperature would be increasing. As the temperature of the star increases, the luminosity also increases. Or if we were reading it from left to right, we could say, as the surface temperature decreases, the luminosity of the star also decreases. In which group of stars would a star with a temperature of 5,000 degrees Kelvin, let's call it Kelvin, and a luminosity of approximately 100 times the sun be classified? So if we find 5,000 right in between 4 and 6, and we want to find a luminosity 100 more times as luminous as our sun, so we would expect to see that in the giants section. That's about it. If we wanted to, if that isn't a typo, if your teacher wants you to find for a temperature of 5,000 degrees Celsius, just remember from our weather unit, pretty easy. You just have to add 273 degrees. So it's a very minuscule amount of difference, but that should probably be Kelvin. I hope you found this video helpful, useful. Enjoy that star in a box, and I'll see you next time.